Okay, I want to have a lecture about basic Heaviside function because I got a lot of feedbacks and the students have problems. So I'm going to do some examples to find the moment and shear distribution in the beam using Heaviside function. So a basic quick review of Heaviside function. Let's say you have a point on the x-axis, point A. This is 0, this x-axis, okay? Then Heaviside of x minus a, this is defined x minus a if x greater or equal to a, and 0 if x is smaller than a. This is just a definition of this particular Heaviside. Put it in bracket. Let's say if you have an x, if you choose an x here, and it turns out this is a beam, in the particular beam problem, but this is a general mathematical theory. So if you have an x here, in this case, x is smaller than a, right? So this argument, every time you want to evaluate the Heaviside, first you evaluate the argument. This argument is negative, right? So the argument, if the argument is negative, or x minus a is x is smaller than a, or arg is equal to negative. Argument means the entirety inside the Heaviside. If that value is negative, then you get 0. So before that, the value of Heaviside is 0. Until you come to the point A and greater than that. In that case, you get x minus a. So that's the function. You see, if you have xy, and this line is y is equal to x minus a. So before xa you have 0, and after xa you have this line. So at the end, the value of Heaviside is this curve. It's kind of like absolute value. It has a sharp point. This has this kind of sharp point. So this is a general thing. It doesn't have anything with beam. This is just mathematics. So every time the point is, every time we want to evaluate Heaviside function, you just come and look at the argument. If the argument is positive, the value of Heaviside is itself, x minus a, parenthesis. If the argument is negative, the value of Heaviside is 0. So this is the basic review of Heaviside definition. So how can we use it with beam to find moment diagram? Let's say in this example we have, let me write it here, use the all possible area of whiteboard. So this is my beam, and this point is pin, this point is roller, and there is a force 2K here. This area, okay, and from here to here is 4 meters. From here to here is 1 meter, and that's 2 kilonewton. And now the question is draw or find moment and shear versus x, where x is a location from left, can be from right. So the way we do this, if you do conventional method, we should first consider this interval, because after this we have a discontinuity. So we consider this interval, this section, we find moment and shear here by writing equilibrium equation for either this part or this part. And then we consider after this roller, right? We consider this, do it again, and then we find two equations for moment. One from here to here, one from here to here. And similar thing, two equations for shear. One from here to here, one from here to here. This is the conventional approach. The Heaviside method, you find one relation for moment, one relation for shear, all across the game. So this is the advantage. You don't need to do interval-based approach. So, let's first do the conventional approach. First, I need to find reaction before I draw the moment diagram. So, FBD of this, let's say this point, this is a different color. This point is A, B, C. So you have a By here, unknown. AX, so we don't have X force, so I don't even write it. No moment, and you have A by. So, for the entire thing as a system, you have negative 2K plus By plus AY is equal to 0, summation of force in Y0, summation of moment around A gives you By times 4, positive negative 2K times 5 is equal to 0. This would give you By is equal to 10K over 4, and you put it there, that's going to be 5K over 2 and 2.5K. You put here, and then AY, so negative 2.5 and 2, negative 2K plus By 2.5K plus AY is equal to 0. Then it's going to be positive half a K, 500, and then go there, AY is negative 0.5K. Right? That's what you get. So this is the external forces. So I here AY is negative 0.5K and By is 2.5K. So now I just erase this to free out some space. Now let's say I want to find shear and moment using conventional method. So first, X between 0 and 4. So you cut this somewhere here, and I draw FBD. So you have negative 0.5K at point A, and this is X. And here you have MX going up, Vx going down, no axial force. And then come back to this point. Right? So here you can say summation of force in Y0, that will give you negative Vx, right, plus whatever this value is, because it's upward, plus. But this value is negative 0.5K. Negative Vx plus negative 0.5K is equal to 0. That means Vx is equal to negative 0.5 kilonewton. This is a shear between x 0 and 4. Let's write it in another color. X between 0, not all, only here, between 0 and 4. Right? Now, let's go to the moment. If you write the moment around this point 0, then you get summation of moment is mx. Look, everything on the right 2k, this does not have anything with the left. So for things here, I just need to consider this into my moment equation. I don't consider the other thing to my moment equation. So you have mx here, and then negative, whatever this force is, 0.5k negative times x. You see, mx positive. This one going clockwise, negative. X times its value, negative, x times its value is also negative. Negative times negative positive is equal to 0. That means moment becomes negative 0.5 kx. Right? If you can see, the derivative of moment is shear. So now it makes sense. This is between 0 and 4. Now let's go here in this area. Let's continue our x. So we have this area. Now, if you consider this area, you can either take left or right. Okay, I take right, because the right is simple. So for that, the free body diagram, this is the non-color. Now x is between 4 and 5. In that case, the free body diagram, you have a 2k, I take it from right. And this distance from here to here is the entire length, which is 5, 4 plus 1, 5, minus x. X now comes to here from left. We extended the x to this point. So that's going to be 5 minus x from here to here. And here you have a moment, like that, internal moment, mx, and shear go up on the right side, vx, no axial force. So this is FED. Now write the equilibrium equation for this part. So you get vx plus vx minus 2k is equal to 0. Vx give you 2 kilonewton. Immediately we know that moment is a 2k times x plus something, a linear function. Now let's find moment. Summation of moments. You can use integration, or you can just directly apply equilibrium equation and find vector moment without doing integration. I recommend this method, equilibrium equation. It makes you a very quick way to compute it. So write moment around this point is 0, equilibrium equation, right? So that gives you mx negative going inward, right? Vx doesn't have a moment, goes through that point. Negative 2k times the distance. The distance is 5 minus x, right? Negative 2k times distance, 5 minus x, is equal to 0. So solving for mx, take it to the right side, mx is equal to negative 2k times negative x, positive 2kx, negative 10k, 5 times 2, negative 10k. This is your moment. As you can see, the derivative of moment with respect to x is shear. See that? Okay. Now, let's put this in an organized way. instead of having all this computation, because we don't have infinite y, unfortunately. So I'm going to summarize my moment equation and shear equation here. So Vx is equal to, if x is between 0 and 4, and if x between 4 and 5, I here and here. So here, before x between 0 and 4, the shear force was negative 2.5 kilonewton. And after 4 to 5, the shear is now 2 kilonewton between 4 and 5. That's for shear. The moment relation is, again, x between 4 and 0, x between 0 and 4, and 4 and 5. Then here we have shear negative 0.5 K. Moment was negative 0.5 Kx. And here we have shear is equal to 2K, 2 kilonewtons. The moment was 2K x minus 10K. So those are my shear moment equation using conventional method. We did in mechanics of material, interval based. Now this is not too hard. Now imagine if you had multiple reactions here, or loading, different kind of loading, then that would be a mess to do all these separate intervals, right? To write all this piecewise continuous function. Now let's do it with Heaviside. So I'm going to erase this. But I keep the question, but I still want to solve it using Heaviside approach and compare it with conventional. They should give exactly the same result. So for Heaviside, what I do, I either pick the left or from the right, and I cut it somewhere to the very end possible to include all the loading. Let's say I cut it here to include all this loading, right, from left. So this is x from left. I cut it from here. So here, if I make FBD of that, or just make it FBD of that part here. So you have a By, which is 2.5 K, and you have a AY, which is negative 0.5 K, negative 0.5 K, and here at this intersection that we cut it, you have an MX, and you have down Vx. So that's all the loading you have here in this example. So the first thing you do in the Heaviside, you cut it either from right or left. Here I took x from left, and try to extend this x such that it includes all kind of loading on the system. Here we have a roller and a support, so it should include both of them. So this is your x. And then once you cut it, then you have moment, shear, axial force. Then you put all this loading, the external loading, 2.5 K, negative 0.5 K, AY, BY. No moment here, it's pin. No force in the x direction, nothing. So that's all you have, right? So here, if you write one moment equation around this point, summation of, let's say this point is A. Summation of this point, A is, if A is here, B is here, C is here, let's say this point is B. Summation of moment around point B with this sign positive is equal to 0, because this part is in equilibrium, right? This is the equation of equilibrium on this point. That will give you already have an mx positive. V is going through that point, no moment. This guy is going to generate a moment, which is force times this distance, right? We know that the force is 2.5 k, but what is this distance? Is this x minus, so this is from here is 4. So this distance, we may think this distance is simply x minus 4. But look, if this section is before this roller, there is no roller at all. So it should be identically 0. So that's the reason we do Heaviside. Because before 4, the argument is negative and this gives 0. It's something like a switch. Right? We added just artificially to make compatible between different sections. So this length is x minus 4 Heaviside, or Heaviside of x minus 4. Now the moment of this force is this force times this distance, negative. So it's going to be negative 2.5 k times x minus 4. So that moment of this force, and now moment of this force is whatever the force is, negative 0.5 k plus the value, in fact this is going this way, right? R cross F, clockwise, so it's negative. Negative, the value of force, negative 0.5 k, times this distance, x. And this distance, x, is always there. We don't need a Heaviside. We could say Heaviside is, but Heaviside is always x, because the argument is always greater than 0. Once it's x is positive, from 0 to anything. And that becomes equal to 0. So you solve for m, so you get one equation that covers these two simultaneously. So you get 1 mx is equal to, take this to the right side, 2.5 k x minus 4. This is going to be positive. If you take it to the right, you have negative 0.5 kx. So this equation is this equation and this equation simultaneously in one equation. So let's say if x is between 0 and 4, then what do I have here? You compute the argument is negative. X is smaller than 4. It's negative, so this is 0. Then what do we get? Negative 0.5 k. That's what we have, right? Now if x is between 4 and 5, this is itself, so Heaviside of that is x minus 4 parentheses times 2.5 k, and you also have this term, negative 0.5 kx. 2.5 k minus half become 2 k x, and 2.5 times 4 become negative 10 k. That's exactly what we had before. You see? But we had one line. For this we had one whiteboard, for this we have one line. So, also for shear, the shear force, if you consider summation of force in y is equal to 0 for this system is in equilibrium, right? What are the forces in y direction? We have a negative v x going down. This is a moment. And then you have a 2.5 k going up. But you put a switch here, x minus 4 to power 0. That's the trick. So if you are before x minus 4, or the argument is negative, this is 0, and this does not exist. And after x4, if x is greater than 4, then this is positive, so it's itself, x minus 4 to power 0 is 1. So you become 2.k positive. So it's just like a switch that brings this 2.k up when you pass it. Then plus ay, so plus ay is negative 0.5k, right, is equal to, this is always there, independent of x, whatever x we have is right there, is equal to 0. Solving for Vx gives you, take this to the other side, Vx is equal to 2.5 k x minus 4 power 0, negative 0.5 k. Now that's my shear force, but this is two equation. This unfolds to this two equation. If you are smaller than 4, this term does not exist. So we get negative 0.5 k. Right? If you are greater than 4, then this becomes 1, 2.5 minus 2, minus 5, 0.5 become 2. So we get this. So this equation is in fact two equations here. Well, this was the simplest possible example. In the next example, I'm going to consider a distributed load.